to discuss about modifications of biomaterials. So far we discussed about biomaterials, biopolymers and many things. So in this topic we will be discussing about modification of biomaterials. So why we have to modify? Ask yourself the question. Anything, whatever is there, it's already, if it is in perfect way also, we still needs to modify. The reason is very simple. To get what we want, okay, to get the property, whatever the desired property what we want, that's why we do modification. Okay, for example, usually if it is a boys, when we buy some bike, we already know that it's perfect, okay, that's why we bought that bike, but yet we do some modification because we want to have some maybe more sound or maybe more different look which is not there for all the bikes and all, okay, depending on our needs. And when it comes to the girl side, even though you are so good looking, you still go for your makeup and all, right? Why? Because you want to look good, more better. So these all things, what it is showing, why I am giving all these examples is that when we need a certain desired properties or characteristics, we have to go for modifications. Similarly, when we need a biomaterial to be used inside our human body, and if I want that material to be with desired properties, then I can go for that particular thing. For example, imagine I need a biodegradability for longer period of time when I am using the biomaterial for bone or any hard tissues, whereas soft tissues requires lesser biodegradation because implants should be there unless the new cells are coming or new tissues are coming. So after once the new tissues come, it should degrade. That's why we are having biodegradable property, right? So if the soft tissue takes time for development, 1 month, then I need a biomaterial to be degradable after 1 month only. If the rigid tissues is taking the time for 3 months, then I have to increase the same biomaterial property, degradable property to the next 3 months. That is, I have to increase its, I have to slow down its rate of biodegradation. So this tunability, this can be done only by the modification of the biomaterial. I hope you understood. Okay, rest everything revolves around this concept itself. Okay, so I'll just go with a little bit faster. So because there is no much extra things to be explained. So biomaterials exhibit various degrees of biocompatibility or compatibility with a harsh environment within living organisms. So various degrees of compatibility. Biodegradability, what I told you, is the same thing. Biocompatibility we are talking here. That's it. They need to be non-reactive chemically and as well as physically with the body. That is about compatibility. That's why we call it as compatibility. They should not react in chemically or physically, as well as integrate when deposited into the tissue. They also integrate with the tissue. They should not cause any deformation or something like that. The extent of compatibility varies based on the applications and the material required. Whatever the based on the applications and as well as the material which is being required, it depends on the the various degrees of biocompatibility. So often modifications to the surface of the biomaterials systems are required to maximize the performance. As I told you in the examples, even though we are better looking, but we still want to see the best out of it. So it's the same thing, even though materials are there, it is giving the property, I want the best performance or maximum performance. So I do modification. Then the surface can be modified in many ways, including plasma modification, applying coatings to the substrate. Same thing what you do for makeup. So surface modification can be used to affect all these properties. Why do I have to make modification? Because I want to increase the surface energy or decrease the surface energy. Okay, and I want to increase the attachment power or decrease it, or biocompatibility. Okay, various degrees of biocompatibility, chemical inertness, lubricity, sterility, asepsis, thrombogenicity. Okay, what do you mean by thrombogenicity? To induce the thrombus. What do you mean by thrombus? Thrombus is something which happens just before the clotting. That clotting that after once the blood, once any injuries happen, the blood will start clotting, right? So that is called as thrombogenicity. There will be due to platelets, this clotting will happen. So to increase the thrombogenicity or to stop the thrombogenicity, all those things, then susceptibility to corrosions, anti-corrosion coatings, next degradation as we discussed, and hydrophilicity, that means water loving property. When I want to use particular material in aqueous environment, I make it as a hydrophilic in nature. In non-aqueous, I make it as hydrophobic. So first one, plasma modification. Plasma modification is one way to alter the surface of the biomaterial to enhance their properties. How? During the plasma modification technique, what happens? Surface is subjected to high levels of excited gases. Okay. So here, high levels of excited gases will hit the surface of the biomaterial. That alters the surface of the biomaterial. So plasmas are generally generated by the help of RF field, that is the radio frequency field. Additionally, additional methods include applying a larger DC voltage also across the electrodes engulf in gas, so that it will high pressure will be there, and that will hit on the materials, so that the materials whole physics will change and its surface chemistry will change. Now the plasma is then used to expose the biomaterial surface, which can break or form chemical bond. If I want some bonds to happen, I will form the bond. If I want some bonds to be not there, I will break that. Depending on my need, I will do that. So this is the result of physical collision or a chemical reactions of the excited gas molecules with the surface. That's how the plasma modification takes place. So this changes the surface chemistry. Because of the surface chemistry, surface energy will be changed, okay, which is one of the material, which is one of the important property which can affect other properties like adhesion, attachment. Adhesion is totally depends on surface energy. Biocompatibility depends on surface energy. Chemical inertness depends on surface energy. Lubricity depends on chemical energy, and also sterilization of a material depends on surface energy. And when I want a particular adhesion to be changed, when I want a particular biocompatibility to be changed, then I just change the surface chemistry with the help of plasma, so that surface energy can be changed, will be changed, and same as the other properties too. Applications in surface functionalization. Why do the applications of the surface modification? Surface functionalization. What do you mean by surface functionalization? You have a surface, you have a material, it has got its surface, and that surface has to get some molecules to be attached so that it will functionalize. That is called surface functionalization. So surface modification techniques have been extensively researched for the applications of the absorbing biological molecules, attaching biological molecules. So surface functionalization can be performed by exposing again to the surfaces of a biomaterial to the RF plasma many gases that can be excited and used to functionalize surfaces for a wide variety of applications. Common techniques include using air plasma, oxygen plasma, and ammonia plasma, as well as other exotic gases, because for inertness we need these particular exotic gases itself. So each gas can have varying effects on the substrate, and these effects decay with the time as reactions molecule in the air and contamination occur. So when you are keep on doing it, so definitely after a lot of after a long period of a time, that surface chemistry which is being changed, that will lose its property, because and then contamination may occur. That's one of the drawback. So argon plasma used for the polymer surface functionalization prior to the bonding. You can have a look at it here. This particular the blue line, which is nothing but argon plasma, which consists argon glass molecules which will be hit with the high pressure on the surface of the biomaterial, and that will change the surface chemistry, and eventually when the surface chemistry changes, surface energy of the material changes, and that will lead to the different properties. Next, that was about the applications as a surface functionalization. Next, plasma treatment to reduce thrombogenesis. That means thrombogenesis is something when you are keeping some thrombogenesis, something clotting. So when I am keeping some biomaterial inside my body, so it should not cause thrombogenesis. So I need to reduce the thrombogenesis thrombogenetic property of that particular material. So plasma treatment to reduce thrombogenesis. So ammonia plasma treatment can be used to attach the amine functional groups. So here amine functional group will be attached on the surface so that can reduce the thrombogenesis. So these functional group lock onto the anticoagulants like heparin, decreasing thrombogenicity. So they will lock onto the anticoagulants. That means they will inhibit the activity of the heparin and like heparin and all. They will decrease the thrombogenicity so that the clotting will not be there. So the third application, plasma treatment for surface cleaning, where a closed discharge plasma treatment is the technique that is used for cleaning contamination from the biomaterial surfaces. Before you implant, just before implanting, you go for cleaning because contamination should not be there. That as a biotechnology students, you know about it. So plasma treatment has been used for various biological evaluation studies to increase the surface energy of a biomaterial surfaces as well as cleaning. Again, same thing. Plasma treatment has also been proposed for sterilization of the biomaterials for potential implants. Sterilization is nothing but cleaning itself. For biotechnology students, it's very easy term to understand. So these are all the contaminants and that can be prevented, washed with the help of a glow plasma discharge, and these bacteria can be removed. Glow discharge plasma made up of atoms or molecules, they will come and hit on the surface. Adsorbed molecules will be there, particles and contaminations will be removed. So they will come and sit here and make sure that they will form a dangling bonds. These dangling bonds will make sure that the surface will be clean. These bonds will not allow bacteria or dust particles to sit here. That was about plasma modification. Next we are having modification by coatings. So two things we told, no? Plasma modification by coating. So that was plasma modification is done. Now the second part of this topic is modification by coatings. Now the modification by coatings in the sense to apply coat. Now so far plasma you are giving some particular gas molecules so that the surface chemistry will change, surface energy will change, other properties will change. Simple. Whereas by modification by coatings, here one extra added one layer of coating will be there in order to get different applications, desired properties for different applications. So modification by materials with the polymer coatings, that is first thing. As a polymer coating we will see. Another method for altering the surface properties of a biomaterial is to coat the surface. So coatings are used in many applications to improve the biocompatibility and alter the properties such as adsorption, lubricity, thrombogenicity, degradation, corrosion and all. For example, if I doesn't want corrosion, so I will coat anti-corrosion materials on this particular coating on the this particular biomaterial, like that. So example, guide wire for coronary angioplasty. I told you a guide wire we use for the coronary angioplasty. So this guide wire will make sure that it will get done, and if any extra this particular plaque built in the arteries, that will that can be removed by this particular guide wire. So guide wires are example of the applications of biomedical coatings. So guide wires are used in coronary angioplasty to correct the effects of coronary artery disease. For example, a disease that allows plaque build up on the wall of the arteries. So if imagine a pipe with a lot of waste, and you to remove that, what we use a particular wire, right, or particular small stuff, so that which can be broken down, all these things. So you are having the guide wires, that is the guide wire threaded up through the femoral artery to the obstructions. So the guide wire guides the balloon catheter to the obstruction, where the catheter is inflated to press the plaque against the arterial walls. So it will make sure that it will build whatever the plaque build up, that will be removed. So guide wires are commonly made from the stainless steel and nitinol and require polymer coatings as surface modification to reduce friction in the arteries. So the coatings of the guide wire can affect the trackability or the ability of a wire to move through the artery without kinking, that or the tactile feel or the ability of a doctor to feel the guide wire's movements and the thrombogenicity of the wire. So to get the desired properties like hydrophobicity, hydrophilicity, we can coat this particular polymer coat on this particular guide wire. So applications we are having hydrophilic coatings to make the surface for water loving property. Hydrophilic coatings can reduce frictions in the arteries up to 83% when compared to bare wires due to their high surface energy. So that is because hydrophilicity is very important for guide wires, because it is surrounded by the blood. So when the hydrophilic coatings come into contact with bodily fluids, they form a waxy surface texture that allows a wire to slide easily through the arteries. So that hydrophilic, it doesn't cause anything, so it can slide easily because it is thing with the this thing. So advantages: guide wires with hydrophilic coatings have increased trackability and are not very thrombogenic in nature. That means they will have a reduced thrombogenicity. They will not cause any clotting effects. That's why those are the advantages. Whereas drawback, however, the low coefficient of the friction increases the risk of the wire slipping and perforating the arteries. If too much hydrophilicity, that can cause the slippery. Because of the slippery, the inside wall can rupture. Hydrophobic coatings. So Teflon and silicone, they are commonly used hydrophobic coatings for coronary guide wires, whereas hydrophobic coatings have a lower surface energy and reduce friction in the arteries by up to 48%. So hydrophobic coatings do not need to be in contact with the fluids to form a slippery texture. They doesn't have to be in contact. So hydrophobic coatings maintain tactile sensation in the artery, giving doctors full control of wire at all the times and reducing the risk of perforation. Whatever the disadvantage is there in hydrophilic nature, that can be overcome by the hydrophobic nature. So though the coatings are more thrombogenic than the hydrophilic coatings, but the disadvantage is here. Whatever the advantage of the hydrophilic, the thrombogenicity was less. Here thrombogenicity is more. And thrombogenicity is due to the proteins in the blood adapting to the hydrophobic environment when they adhere to the coatings. That we know the definition. So next topic is the role of nanotechnology in this particular tissue engineering that we will discuss, or in biomaterials that we will discuss in the next class.